everyone, welcome to The Explainer. Today we're going to unpack something that is absolutely foundational for the future of digital architecture. We're diving into the Omi Agreement Doctrine, specifically the actual anatomy of an open-world object. What we're exploring is exactly how the OMI protocol, also known as the Omicron Object Model, unlocks this incredibly seamless, practically zero-cost adoption for building open worlds. And you know the absolute best part? It pulls this whole thing off based entirely on a pure structural concept of agreement.
So think about the core tension we face in our digital age right now. How do independent systems actually agree on what's true when there's no central server running the show? I mean, when we're operating in these massive, decentralized, open worlds, no single platform owns the truth, right? There's no giant master database in the sky dictating exactly what just happened. So how do a bunch of totally independent peers, different computers, entirely different portals, look at the exact same digital object and fundamentally agree on its state?
Well, to solve this, we actually have to take our everyday normal definition of agreement and totally throw it out the window. In OmiEd, agreement isn't a feeling. It's not some democratic group vote, and it's definitely not a top-down platform decision. It's not even just the fact that, something successfully rendered on your screen. Agreement here is a strict structural event. It's the exact literal moment an open-world declaration becomes bounded, validated, replayable, and inspectable. In OmiEd, this structural agreement actually has to happen before evaluation even kicks in.
We've got a lot of fascinating ground to cover today, but don't worry, we have a clear roadmap. We'll hit 1, the meaning of agreement, 2, the minimal object boundary, and 3, decoding the truth row. Then we'll look at 4, the lightweight 128-bit frame, 5, materializing the object, and wrap it all up with 6, open worlds, seamless trust. Let's dissect this from the outside in. All right, kicking things off with Section 1, the meaning of agreement, moving beyond centralized authority. So think about how things usually work. In a traditional framework, the whole philosophy is pretty simple. The app owns the object. The app, the server, or the database, they're the bosses telling you what's true. But the Omi protocol, it completely flips the script. In Omi, the system doesn't own the object at all. Instead, the object has a boundary, a transition, and a receipt. Imagine a game of chess. Instead of the game's server owning the chess piece itself holds its own verifiable history. The hard proof of what happened is baked right into the object's very structure, totally independent of whatever app happens to be displaying it at the time.
Moving right along to Section 2, the minimal object boundary, creating the enclosure. Okay, so OMI starts with literally the simplest boundary you can imagine, Omi --, or symbolically just an O, 3 hyphens, and another O. Now, the really fascinating thing here is that this hyphen field in the middle, it isn't just empty space, it's not just decorative formatting. It is the 0 point. It's the join field, the structural bus, the gravity bridge that bookends a relation. So an object in OMI isn't just the stuff on the left side or the right side, it's this entire bounded relation that can actually be passed around, validated, and inspected by anyone. Which brings us to Section 3, decoding the truth row, the formula of bounded trust. Okay, look at this. Every single accepted OMI frame yields exactly one truth row. It's just 3 incredibly simple variables, LL, NN, and MM. I know, it looks super abstract right now, but believe me, this tiny little row is the absolute engine of open world agreement. Let's break those variables down so they make sense. NN is the antecedent state, basically where you started. MN is the consequent state, which is where you ended up. So getting from NN to MM, that's the actual transition being proven. Pretty straightforward, right? But what about LL? Well, think of LL kind of like a super sophisticated mail sorting algorithm. NN and MM prove that a package moved from point A to point B. But LL is what guarantees that package gets routed to the exact right destination. It acts like a lens that simply selects how and where a proven transition is going to land. But remember, OMI doesn't just blindly accept any declaration you throw at it. It follows a really strict step-by-step pipeline to ensure this seamless trust across the entire network. First up, the frame absolutely has to pass validation. Second, the Delta and Fano systems step in to actually resolve that transition from NN to MM. And third, and honestly, this is the most crucial part, a receipt records the accepted envelope. See, LL, that mail sorting algorithm we just talked about, it is not the boss here. LL cannot just accept a transition on its own. Only the receipt securely validates and authorizes it. LL is literally just routing the delivery after the receipt has already signed for the package. Let's slide into Section 4, The lightweight 128-bit frame, the engine of low cost.
128. That is the total number of bits in a standard canonical Omi frame. We're talking about just 8 16-bit segments. Just to put that into perspective for a second, that is vastly smaller than a single empty text message on your phone. Because it is so microscopically small, Omi is able to compress all this complex topology and incidence into this tiny frame-addressable structure. Processing these frames across millions of independent peers requires practically zero bandwidth or computing power. It's a total game changer. It enables massive scalability and lowers the barrier to entry to essentially nothing.
And it gets even cooler. Inside that tiny 128-bit frame, our L variable, it's just an 8-bit value. And it's split perfectly down the middle into two 4-bit halves, what we call nibbles. The high nibble carries the context, like what lens family or peer scope we're currently in. The low nibble, on the other hand, acts as your execution slot selector. The sheer beauty of this design is that the shell doesn't branch on meaning, it only extracts structure. It gives the execution envelope this perfectly clean, independent structure that takes basically zero processing power to route. And that drastically drives down network costs for everyone. All right, section 5, materializing the object, from logic to projection. Okay, so we've got this ultra-lightweight, perfectly validated frame. But where does that proven transition actually go? Where does it land? Well, it lands right here in the 0xe execution band. Remember that low nibble of the LL variable we literally just looked at? It actually acts as an address pointing directly into this execution band. This is the exact spot where object transformations finally materialize. It's where abstract logic turns into something a system can physically project onto your screen, whether that means updating a web page's DOM or drawing a full 3D asset onto a canvas. Now, take a look at the really elegant folded topology of that execution band. Since the selector is just a 4-bit nibble, you get exactly 16 possible command slots, no more, no less. And Omi splits this manifold up so cleanly. 12 of those slots are inner-packed materializers. They're doing all the heavy lifting, the dense work of actually transforming the object. The remaining 4 slots, they handle the outer controller vertices. Basically, they manage how you actually view the object, like changing your camera angle or shifting your perspective in a 3D environment. It is just incredibly highly structured logic, all packed perfectly into 16 tiny little slots.
And finally, section 6, open worlds, seamless trust, the future of decentralized agreement.
The quote you're seeing right now, this is the absolute core product promise of the entire Omi protocol. Omi lets people save, share, verify, and move objects without losing history or context. Because of that ridiculously tiny 128-bit frame, and because agreement is a structural event that happens before evaluation even starts, you don't actually need to trust the app displaying the object anymore. You just trust the object itself. You can literally take an asset from one portal, move it to a completely different, totally independently built system, and the entire history, the boundaries, and the fundamental truth of that object will travel securely right along with it. So we've seen how Omi just completely strips away the need for these heavy, expensive, centralized servers, replacing them with a tiny 128-bit envelope that mathematically proves truth across independent systems. It's wild to think about. When agreement natively comes before evaluation, and when participating in this massive network costs almost absolutely nothing in computing power, what kind of open world are you going to build? Thanks so much for joining me on this explainer today. I really hope it sparks some incredible ideas for you. Catch you next time.